Lecture number 26, CS218, Data Structures and Algorithms. Assalamu alaikum. Let's start. We are working with graphs and we are using chapter 8 of book 4. In the last lecture, we found the weight matrix for a weighted digraph. We executed the SPA on a weighted digraph and we investigated the time and space complexities of the shortest path algorithm. Our topic today is graph traversal. We will discuss both the algorithms and the data structures involved. Search algorithms. The sequence generated by graph traversal greatly depends on the starting node. If the starting node is changed, the sequence of traversal will change. Traversal is mostly done to find a path from a source node S to a destination node D, if such a path exists. And that is why these traversal algorithms are called search algorithms, because you are searching for a path. There are two algorithms that help traverse graphs. One is called the depth first search or DFS, and the other is called breadth first search or BFS. Breadth first search. This traversal technique uses a queue. Each node has a status variable. If status is 1, the node has not been added to the queue. If status is 2, the node has been added to the queue where it is waiting to be visited. If status is 3, the node has been visited. We have to keep track of the status of nodes because, as you remember, traversal is visiting every node exactly once. If we don't keep track of status, we run the risk of visiting a node more than once, which would go against the definition of traversal. BFS algorithm. The input is a graph G stored in memory and a starting node X. Step 1. Set status equal 1 for all nodes. None of them has been visited yet. None of them has been added to the queue. 2. Put X in queue called Q. Set status equals 2 for X. Step 3. Repeat until Q is empty. A. DQ from Q. Let this node be N. Visit N. Set status equals 3 for N. B. NQ all neighbors of N whose status is 1 and set status equal to 2 for them. 4. Exit. Find a path from A to J in the diagram shown here. The first step is to create an adjacency list in which we list the nodes and their neighbors. In the same list, we initialize status variables of all the nodes. This is the table that is generated. A has neighbors B, C and F. B has neighbors C, G. What I am doing is I am looking at every node and listing the nodes to which an arrow goes from the current node. See, an arrow goes from C to F. So the neighbor of C is F. From D, I can go to C only. So the neighbor is C. From E, I can go to C, D and J. and they are the neighbors. From F, I can go to D only. From G, I can go to C and E. From J, I can go to D and K. And from K, I can move to E and G. Currently, none of the nodes has been added to the queue, so the status variables are initialized to 1. We maintain a queue called queue. In addition, we maintain a list O for origin, which keeps the name of the node which led to the insertion of this node in queue. We enqueue the source node. We are asked to find a path from A to J. So A is the source node. We put A in queue at index 0. The corresponding entry for the source node in O is always null. So you can see that the corresponding entry for A in O is null. Previously you had seen that the queue was empty, the front pointer was null and the rear pointer was null. Whenever we enqueue, we advance the rear pointer because we are adding to the rear, and whenever we dequeue, we advance the front pointer because we are deleting from the front. Right now, since the front and the rear were both none, we will initialize both of them to 0. This shows that the queue extends from A to A, or there is only one element in the queue. You can also see that the status variable of A has been changed to 2. We visit the node at the head of the queue after dequeuing it. So since we are dequeuing, we advance the front pointer and that becomes 1. Now we have front greater than rear. This is one of the conditions showing that the queue is empty. The first condition we've already seen. If front is none and rear is none, the queue is empty. Or if front is greater than rear, the queue is empty. And you can see that the status variable of A has become 3. We add all neighbors of the dequeued node, which is A, that have not yet been added to the queue. There are 3 neighbors of A, B, C and F. Since we are in queuing, we are going to advance the rear variable or the R variable. You can see that the status of B, C and F have been changed to 2. One thing to note here is that in the origin list or the O list, we are inserting A for all of these nodes B, C and F. This is noting that these nodes were pushed into the queue after the dequeuing of A. The queue extends from B to F, front is 1 and rear is 3. Again, we dequeue a node and we visit it. So we advance front becomes 2, B is dequeued and the status of B becomes 3. We add neighbors of the dequeued node which have not yet been added. B has 2 neighbors, C and G. C has already been added, so we add G and the status variable of G becomes 2. The queue now exists from C to G. We have advanced the rear variable. Another thing to note is that for G, the origin entry or the O entry is B because it was enqueued after the dequeuing of B. Now we dequeue C. The status of C becomes 3. Front is advanced. C has only one neighbor F, and that is already part of the queue. That is why we are not enqueuing anybody at this stage. We dequeue F, status of F becomes 3, front is advanced. We now add neighbors of F that have not yet been queued. F has one neighbor D, so the status variable of D is changed to 2. D is added to the queue. The queue now exists from G to D. For D, the corresponding entry in O is F because it was enqueued after the dequeuing of F. Now we visit G. Status of G becomes 3. Front is advanced. We add all neighbors of the dequeued node, which is G, that have not yet been added to the queue. G has two neighbors C and E. C has already been added, so we enqueue E. And the corresponding entry for E in O is G because it is enqueued after the dequeuing of G. The queue now exists from D to E. You can see that we have advanced the rear variable. Now we dequeue D. Status of D become 3 and front pointer is advanced. D has only one neighbor, which is C, that is already part of the queue, so we do not add it to the queue. We dequeue E and we visit it, so status of E becomes 3. Front pointer has advanced, and since F is 7 and R is 6, you can see that the queue is empty. Now we add neighbors of E that have not yet been added to the queue. E has 3 neighbors C, D and J. Out of these only J has not yet been added, so it is enqueued and the queue exists from J to J after the advancement of the rear variable. J was enqueued after the dequeuing of E, so the corresponding entry in O is E. Now we dequeue J. The status of J becomes 3. And as soon as the destination is visited, we stop executing breadth first search. We now read Q and O, starting from the destination in the manner shown here. Start from J. Go to corresponding entry in O. You get to E. Now find E in Q. Here it is. Go to the corresponding entry in O. We come to G. Find G in Q. Here it is. Go to the corresponding entry in O and you come to B. Find B in Q. Here it is. Go to the corresponding entry in O and you have A. Find A in Q and go to the corresponding entry in O. When you reach the null character, the path is complete. So what did we get from this mannerism? We got this sequence from J to E, from E to G, from G to B, from B to A, and from A to null. Now what remains is that we reverse this path. and this is the path from A to J. If no path exists between source and destination, we will finish breadth first search but will not be able to enqueue the destination node. So when the queue will be empty, we will come out of the loop of BFS and we will exit without a path. Analysis of breadth first search. The worst case happens when either there is no path from source to destination or the destination is the last node to be enqueued. In the worst case, the loop in breadth first search runs as many times as the number of nodes, which is n. In the body of the loop, we enqueue and dequeue, which takes O1 time. We update the status fields of neighbors of the dequeued node, but this does not take a significant amount of time and hence can be ignored. From this we can conclude that the time taken by breadth first search is O(n). Breadth first search uses a Python list of length n to keep status values of all nodes. It uses a queue implemented in a Python list and another Python list for O. In the worst case, the length of both Q and O is n. From this we can conclude that the space taken by BFS is ON2. Q for BFS. A class Q and O is implemented for breadth first search. This class creates an object that has two lists, one each for Q and O. F and R variables for Q are also maintained within this object. A function is provided to see whether the queue in the object is empty. This is true whenever both F and R are none or when F is greater than R. A function is provided to enqueue a node in the queue of the object. This function updates both Q and O and also updates R. A function is provided to dequeue a node from the queue of the object. This function updates F and returns the dequeued value. A function is provided to read Q and O and provide the path if it exists. Depth first search or DFS. This traversal technique uses a stack. Each node has a status variable. If status is 1, the node has not been added to the stack. If status is 2, the node has been added to the stack where it is waiting to be visited. If status is 3, the node has been visited. DFS algorithm. The input is a graph G stored in memory and a starting node X. Step 1. Set status equal to 1 for all nodes. 2. Push X in stack S. Set status equal to 2 for X. 3. Repeat until S is empty. A. Pop from S. Let this node be N. Visit N. Set status equal to 3 for N. B. Push all neighbors of N whose status is 1 and set status equal to 2 for them. 4. Exit. Find all nodes reachable from J. A node is reachable from J if you have a path from J to this node. The first step is creation of an adjacency list and initialization of status variables. If you are present at node A, see which nodes have edges from A to them. Like you have an arrow from A to B, an arrow from A to C, and an arrow from A to F. So you say that the neighbors of A are B, C, and F. From B you can get to C and G. From C you can go to F. From D you can go to C. From E, you can go to C, D, and J. From F, you can go to D. From G, you can go to C and E. From J, you can go to D and K. And from K, you can go to E and G. We maintain the stack S, and you can see that the stack is empty right now. We push the source node onto the stack. We are asked to find nodes that are reachable from J, so the source node is J. We push J onto the stack and the status of J becomes 2. We visit the node at the top of the stack after popping it out. So J is popped out, status of J becomes 3. We push all neighbors of the node we popped out that have not yet been added to the stack. J has 2 neighbors, D and K. So D and K are both pushed one after the other onto the stack. Their status variables becomes 2. Now we pop from the stack and we get K. So the status of K becomes 3. Look at the neighbors of K that have not yet been pushed to the stack. K has 2 neighbors, E and G, and E and G are added to the stack and their statuses are changed to 2. Now we pop the top of the stack and we get G, and status of G becomes 3. Now we push the neighbors of G that have not yet been pushed onto the stack. E has already been pushed, but C hasn't been pushed, so we push C and the status of C becomes 2. We pop C from the stack and the status of C becomes 3. We push neighbors of C which have not yet been pushed onto the stack, and C has one neighbor F. Status of F becomes 2. We pop top of the stack, we get F, and status of F becomes 3. F has one neighbor D which has already been added to the stack. So we do not push any node onto the stack for F. We pop from the stack, we get E. Status of E becomes 3. E has 3 neighbors, C, D, and J. All of them have been pushed to the stack before, so we do not push any further node for E. We pop from the stack, we get D. Status of D becomes 3. You can see that the stack is now empty. And D has only one neighbor. The neighbor is C, which has already been pushed onto the stack, so we don't push it. The stack remains empty. Now that we have come out of the loop of the depth first search, the sequence of nodes popped out of the stack is a list of all nodes that are reachable from the source node. In our case, it is J. You can see that this sequence does not include A, it does not include B. So these two nodes are not reachable from J, or you do not have a path from J to these nodes. Analysis of depth first search. The worst case happens when all nodes are reachable from the source node. In the worst case, the loop in DFS runs as many times as the number of nodes n. In the body of the loop, we push and pop, which take O1 time. We update the status fields of neighbors of the popped node, but this does not take a significant amount of time and hence can be ignored. So we deduce that the time taken is O(n) for depth first search. It uses a Python list of length n to keep status variables for all nodes. It uses a stack implemented in a Python list. In the worst case, the length of S is n minus 1. So the space complexity for DFS is O(n). Using Python dictionary to store graphs. Each node has a name. If we keep nodes in a list, we must search in the list to find a node by name, note its index in the list, and change the value at this index in the status list. This search for the node takes O(n) time in the worst case. If we store an adjacency matrix, we must traverse the whole row for a node to note its neighbors and change their status values. This traversal of the row of the adjacency matrix takes O(n) time. The dictionary can be used to store graphs in memory. Dictionaries are hash tables, a data structure that takes O(1) time to search for a data item. When the graph traversal algorithms were implemented in Python, I used dictionary to provide input. This is how I provided my nodes list. In this dictionary, I am assigning a value to each of the node names. Now, when I am provided a name, I find the value corresponding to it from this dictionary, and then I go to this index in the status list and change the value accordingly. So if I am given the node C, I will change status 2, and if I am given the name G, I will change status 6. So in this way, I avoid having to search for the node name in a list. The other dictionary that I have implemented is for the adjacency list. Here I provide a string which carries the names of neighbors for each node. So when I am given the node D, the adjacency list is read from this dictionary. The neighbor is C. If I am given the node E, the adjacency list is a string of neighbor names C, D, and J. Your homework is to find a path from A to I in the given diagram. And since you're asked to find a path, you will have to employ breadth first search. The second part of this homework is to find all nodes reachable from A, and since you are asking about reachable nodes, you will have to use depth first search. What did we learn today? We explored algorithms for graph traversal. We looked at data structures that facilitate graph traversal algorithms. And we investigated time and space complexities of graph traversal algorithms. In the end, read the book, do the homework. It will be very good exercise and you will understand the algorithms better. Note your questions for the online session, and if you have any suggestions, write me an email. Take care. Allah Hafiz.